Okay, shall we start again? Okay, so the second part, I'm going to show you how in practice we can use PEGs and parser combinators, particular PetitParser, to practically build not just a parser, but an interpreter for a language like SPL. So I'm just going to, it's all integrated into the current build, so you can just download for your platform. It runs on Windows, Linux, Mac, as you will. So we'll just download that. And fire it up. So basically you just have to run the app. I think it might be slightly different on Windows and Linux, but it should be basically that. Okay. And this is a Smalltalk environment, a little bit different from ones you might have seen before. And it has a completely integrated into it a complete notebook, so a book explaining the system. You can have playgrounds, etc., for executing code. So you can evaluate code on the fly. You can write notes. It's like a complete notebook. You have a coding environment, which looks a little bit like what you're used to. So you can see all the packages and categories and methods and classes and so on. We'll be working with that. It's fully integrated with Git, actually, because I downloaded the pre-built version. We don't see any Git repositories here yet, but when I'm working with a build, I'm always syncing everything to Git. We can explore code changes, monitor what's going on in the system. We can explore the file system itself. And we can also default back to the original ferromorphic environment with its tools, which look very different. But we rarely have to do that anymore because more and more tools are available in GT itself. So if you want to play with this, just start by going to the Glamorous Toolkit book and scroll down a little bit, and you'll find the PetitParser SPL case study, which is here. And I'm just going to go directly to the slideshow and show you from there things. But all of the stuff is documented in some detail. So here are all the steps that we're going to look at. What's SPL? So this is actually set up for people who are not part of this course, so they can find out what is SPL and PetitParser. Scanless parsing, debugging rules, extracting a parser class, testing, and so on, and actually building an interpreter with that. But we'll explore this from the slideshow. So what's PetitParser? We saw that briefly. We model parsers as composable objects. So here's a number parser. If I evaluate this, I get a parser that parses digits, and actually a series of digits. So this is a digit parser here. If I evaluate this guy, I get a parser that will parse individual digits. And here I'll parse more than them, so I'm actually composing each of these as an object. Then I turn this thing into a token, and then with an action, I take that token and turn that into a number. Here's an addition parser. It looks for a number followed by a plus. So plus as parser, that's a parser as well. And what the as parser action does, it's just a factory method, and it's going to build a literal node that will actually parse, look for and eat a single plus. And now I can evaluate this whole thing. So here I've built 2 parsers. And now I'm going to parse 3 plus 4. And the actions are actually going to compute the result, which is 7. So there's PetitParser in a nutshell. We're going to be using this framework to build a parser and an interpreter for SPL. So we're going to have little parsers for every tiny little piece of SPL, compose them all together into one big parser for SPL programs with actions. And what the actions are going to do, they're going to build an abstract syntax tree, and that syntax tree actually will later on be executable. What we do with it in the back end can vary from compiler to compiler, interpreter to interpreter. What we're going to do is we're going to have a small step operational semantics. I'll tell you later more about what that is. But that means that when we execute a program, we have, like in the lambda calculus, we can take a single step, reducing a program, actually transforming the AST step by step until it reduces to a final single result. And that's the idea. We could have done many other things. I could have taken a visitor over the abstract syntax tree and generated Java bytecode. Or I could have generated another intermediate representation like SSL, so I can do analysis on it. But you can do other things with the intermediate results, for example, to pretty print or to do syntax highlighting or to do program analysis. Many things can be done in the back end. But what we're just going to do is implement an interpreter. There's the SPL grammar that you've seen before. Timo has kindly given us a grammar which has very nice properties. So what is it, right? The recursion is nice. There's not much ambiguity here, and it's just very easy to implement directly. So it doesn't have any nasty things that we know from real languages. Here's a tiny example of SPL. So what's important in SPL is it's almost a straight line language. It has if, then, else's and while loops. It doesn't have any functions. It has nested blocks. So the question is whether we need scoped environments. But I made the simplifying assumption we don't actually need them unless we're going to start shadowing variables. We can just assume there's a single environment of variables. So that makes the semantics of the language quite simple. You can actually implement some real programs. So here's a factorial program. I make the argument part of the program itself, but the output is going to be printed out. Okay, so the first thing we have to do is we want to do the lexical analysis. But since PetitParser and PEGs, they're scannerless parsers, we just use the same framework for parsing the tokens. So we introduce parsing expressions also for our tokens. So we do that first. In PetitParser, if you want to have a parser for a string, you just send the string the message as parser. And it's just a factory method. So it'll build the right thing for us. So this is a parser that will only parse the string true. This will parse the string false. And now we create a Boolean. That's a parser that will parse either true or false. And there it succeeds. And it will also parse this, for example. But it will ignore the XXX. If, however, we say Boolean end parse, that will fail because it won't consume the XXX. More lexemes. We have integers and floats and strings. Now we start using some of the features that we saw before, optional and plus. So what's an integer? I can have multiple digits. I have a possible minus sign, and there is no period after the last digit. So notice, these consume stuff. This does not. This is the semantic predicate, the one that checks that there is no plus, no dot. If there is a dot following, this will fail. Okay? So here I will parse this. I can also parse 42.0, but it will fail because I did not expect a dot here. Here I have, a float, and it does expect a dot. So float will parse this. Notice what we're getting out is just a really primitive kind of AST. So just listing collections of, so I can view it as a kind of a poor man's syntax tree. So I just have collections of characters and strings. There's no special nodes that I've defined. Now, if I want to parse numbers, they could be integers or floats. And notice here we can have backtracking. So if I want to parse minus 3.14, what's going to happen? I first try integer. It will match up to the 3, and then it'll see there's a dot. So it will fail at the dot as parser not. This will fail, and it'll backtrack. It'll start parsing all over again, and then finally succeed with the float. Of course, we could refactor the grammar to avoid the backtracking, or we could optimize the grammar that will add some memoization, but there are very few cases where we have backtracking in the grammar, so I don't even bother. It's not a real performance issue. Again, stop me if there's anything if I go too fast. But I think most of this should be fairly straightforward. Now, I mentioned, so here's another case where I use the not. Here are all the keywords in SPL, and to match them, I want to match var as a parser for var, a parser for if, and so on. But each of these should not be followed by any further characters. If they are, so for example, Andy is an identifier. So it's not a keyword. So I succeed with keyword up into here, and then keyword will fail, so keyword not will succeed. And then I start parsing here because this doesn't consume any input, and then I will continue executing there. If on the other hand I have this, that should fail.
Oscar,
yes.
Could you please go one slide back?
Yep. Yeah, that would be more intelligent. So I could do this, and that would make more sense. And because the two are disjoint, semantically, it's going to be equivalent. But now what's interesting is I can probably get rid of this with your suggestion. Yeah. So by rewriting the grammar somewhat, you can get rid of some backtracking. Oh, there's still going to be backtracking here. Because what happens here? This should be an integer. Yeah, it won't be a float. Yeah, because this is required for the floats. Yeah, there's some rewriting that we could do. So. Okay. Okay, so far? Okay, yes, Whitespace. So here's a string. We don't have nested strings, so it's super easy. We get a parser for a double quote. Then we eat as many. Negate is different than not. So not doesn't consume something. Negate is one that succeeds where the previous parser would fail, but it does consume. So here we consume something which is not a quote. I got a little bit confused at the beginning, and I had some bugs because I was mixing up negate and not. So why am I not consuming? Oh, right, I should have used negate, not. And then I have plus any number of those. Again, we're building parsers out of parsers. And you can actually see these things. So let's inspect that guy. Oh, this is actually kind of small. But here we can see that it's built up of, we can actually explore the tree of parsers that are built up. Now we have a print statement. And here we want print, and then we want to trim that. So there could be whitespace. So what trim does is it takes a parser and decorates it so it will consume whitespace before or after. And you can modify that to be only before or only after, or you can control what is considered to be white space. So do you want to say only spaces but not tabs, or carriage returns but not line feeds? Yes?
How do you handle the empty string?
In what sense?
Like, I see that there is negate plus in the string definition in the line above.
Oh, yes, you're right. That's a mistake. So this should then be a failure. Thank you. Very good. As I said, I didn't have a test suite. You gave me a grammar, but no test suite. Thank you. Yes, absolutely correct. It should be star, not a plus. So we can handle empty strings. There's some tools for debugging as well. So here, if we run this code, it's almost the same as before. It's going to fail. And we're going to ask ourselves, why does it fail? So what we're doing is we're inspecting the failure here. And if we double-click on that, we can see a view, which is the view of the stream state. And we see a message here. We expected a quote. What does that mean? So we can continue. So we can actually inspect the trace of what happened and where it failed. So it actually succeeded in matching print. And then it failed because it was expecting a double quote. Well, let's look back. Yeah, print and then string. Okay, there's the problem. What we should have done here is we should have allowed for some possible white space. And now it does parse. So the debugging tool is kind of primitive, but you have these nice views where you can actually step through and trace and see where it failed. And usually, if you have a failure that's in a complex program, what you can do is try and narrow down where it's failing and then just grab the parser that's failing on that part and debug that. So you don't have to debug the whole program. You say, oh, I'm having problems in print statements. So let's just see, I'm not debugging a whole SPL program. I'm just debugging the print statement parser. And that's super convenient. Because typically when you're building a parser for a large language, you have to run the parser on the whole thing. And it's not easy to just parse a little bit. And you can debug just expressions and ignore statements. By the way, this is one of the key features of the Glamorous Toolkit, which is that you can, what these views here are inspectors. So if you use an environment like IntelliJ and you have a debugging error, the debugger will pop up and you can inspect an object. And what you get typically is a view like this. This is a raw view. You can walk through the tree and you get one view and that's it. In GT, it's very easy to build new kinds of views. So here, for example, when we get this, see, there's an execration. This is just an object. So here's the raw view, but what I want is a different kind of a view. And this object that I'm inspecting is a debug result. And each of these have dedicated views, which are implemented in a little method, which is typically fewer lines of code than this. So it looks a little bit mysterious here, but there's actually not that much going on here. And you can reuse these widgets to build views that you like. And we'll see that when we start inspecting the results of the SPL programs. Okay. We iteratively proceed building the SPL grammar as a script. So here we have a recursive expression. So we start with Booleans and numbers. I didn't put strings here. Here we have expressions, and we have an expression statement. And here's a very simple SPL program. So this is a partial parser for SPL written as a script. And it parses part of SPL. Well, clearly this is not going to scale because we can't write tests. We can't reuse the results very easily. So what we would like is to turn this thing into a, wait a moment, I'm maybe getting ahead of myself. What we'd like to do is we'd like to turn this into a class. We can extract a class from a script. Let me see if I can just zoom in a bit here. So this was our unresolved node. Here's our parser. So if we have a script, right, that produces a parser, here's the parser that we get. Here's the tree. It's a little bit hard to see. Maybe I can pop that open in a new window. Yeah, so we actually get it. This is just another view, which has its own code that it's actually live as well, so you can actually manipulate this. So there's a visual representation of the parser we have so far. But what we'd like is we'd like to turn this into a class. So there's a refactoring tool bit in here. So we just say extract PetitParser class for all sorts of things like this. So I heard you will call this my SPL, my first SPL parser, and we accept that, and there's the refactoring that's going to be performed, and it's done. So the refactoring is computed. It's going to take all of these bits and pieces, turn each parser into a method and also into a slot, so an instance variable, and there we have it. And now we can evaluate this. There's the parser again, and here it's working. And what is this guy? This is now a class here. A class with a superclass, which is PetitParser thingy. We have for every single parser, we have a method that will compute that parser, and we also have a slot where that parser is cached. So we only have to compute it once. So that's what's going to be generated automatically. And once we've done that, once we've created the first class version, then we can continue working with that and start writing tests and so on. So what do tests look like? Tests in GT look like tests in any testing framework, with one slight difference that we'll see in a moment. So we have a class called grammar examples. So this is a whole bunch of tests that I've defined here. And here's one of them. I take as input a while program source. Here's a little while program in SPL. And what I'm going to do is I'm going to try and parse it with the declaration parser. And I expect that to fail because it's not a declaration. It's also not a statement, but it is a program. So here I have different assertions. I assert that this will fail, that will fail, but this will parse. So this looks like pretty much like any unit testing framework. I have different kinds of asserts here. The only thing that's new is that the result is returned. So that means that a test in GT is an example object. So every test is a method that not only tests something, but it returns an object, which can then be used as input, as a fixture for another test, another example. This means that you can compose tests. This is very, very powerful. It's also useful because the examples are available. You can stick them into notebooks, into documentation, and you can explore them. So usually if tests are only useful if they fail, right? Because a failing test is something you can debug. But a passing test just says it's green, then yeah, what can I do with that? By turning a test into example, a green test is also useful, because you can take the result and explore it. So you can have lots of nice little examples that you can then explore and use to build documentation and create narratives. Okay, so we have a whole bunch of these guys. In fact, some of them are composed, not many of them. Most of these are super simple tests. So here's the map showing which is composed out of others. So in this case, there's almost no composition happening here. But those are all the tests, and we can run them here. So we have 37 just grammar tests that all pass green. And we can explore any of them if one of those looks interesting to you, like the Fibonacci program, then we can run it and see what the result is. Good. Okay, now we have a grammar. So the grammar consists of a bunch of methods, each of which returns a parser, but there are no actions. Now what we could do is we could add actions to them. But maybe we want different parsers that do different things with different actions. So what we'll do, instead of adding actions directly to this guy, we'll create a subclass. And the subclass will just inherit all of those nice parsers, and it will decorate them with additional actions. So this is what the SPL parser looks like. Every method looks pretty much like this. So what's the print statement parser? Well, it's the super print statement parser, the one I inherit, decorated with a semantic action or an action. And in this case, what I'm going to do, every one of these is going to create an AST node. So I'm going to have an SPL print statement node, and it's going to, what it's interested in, where's the super print statement is here, so we can open up the code bubbles to see what I'm inheriting. So this is the code I'm inheriting, and I don't care about the print, I don't care about all I care about is what the string is. So that's why I say, give me the second part of the node, that's the string, and stick it into a new print statement node. Here's the print statement, and a print statement just has the, it inherits from a superclass. It has an expression. So that's all there is. So I'm just creating nodes. So every rule is just going to create a node. So this is a really, really boring class. And I have a whole bunch of different, let's have a look at this guy. Oops. Here's SPL statement. Let's open up the class view. So here we see there's a hierarchy here of nodes, a whole bunch of different nodes here. Actually, I think we see them in the next slide. So this is the AST hierarchy that I built. So for every kind of entity that we have in SPL, we'll have an AST node. Here's the abstract one at the top, with a few basic methods that have been defined. Some of them have default values, and some of them have, let me see, there must be some that are abstract, right? So when we actually run the interpreter, here's an abstract method. In Smalltalk, an abstract method is one that invokes self-subclass responsibility. So if that's ever called, you get an exception saying, hey, you should have implemented this method. So that's what I do here. So I have an abstract class at the top, then we have declarations, and so on. Each of these has a factory method for creating an instance and for populating its state. Okay. So far, we've got the grammar. We can recognize SPL programs. We've done the second part, which is the parser, inherits from the grammar, adds additional actions that take the poor man's syntax trees that we get by default, and extracts the interesting part and builds actual AST nodes for our classes. So now we get a tree of objects representing an SPL program. Now what are we going to do with this? We could do many things. We could have a visitor to walk it, to pretty print it. We could walk it and generate some other intermediate representation. We could use LLVM. We could generate Java bytecode. We could do all sorts of things. Instead, what we'll do is implement an interpreter in a way that is actually kind of standard in programming language semantics. And the idea is to define an operational semantics that's called structural operational semantics using a step-by-step transformation of the program. So just like lambda calculus, I don't know who's seen lambda calculus before? A few of you. Okay, well, the lambda calculus is a very simple language, and the semantics is defined by reduction steps. You have a lambda program, and you can do an alpha reduction or a beta reduction, an alpha conversion or a beta reduction, and then you convert step by step the program into other forms until it terminates or it doesn't. So we're going to do the same thing. Our representations are the abstract syntax tree, and whenever we get an abstract syntax tree, we can do a single step to reduce it to a simpler program. And sometimes, like in the case of a while statement, we actually transform the program into a slightly different program. And we can keep transforming it until we get to the end and there's nothing left to execute. So that's the idea. How do we do this? Let's go back here. There's an abstract method here that's called step in context. How do we execute an SPL program? What is the state of an SPL program? There are three pieces of information. One is the rest of the code. So this is what has to be executed. Two, we have the environment. These are the variables that have been defined and have some values. And three, we have the output. That's what we've printed so far. That's it. So that's a context. So if I have an SPL program and I want to execute it, I create a context with an empty environment and an empty output, and then I start step by step reducing the code, the rest of the code, which is the abstract syntax tree, to new versions, updating the environment and updating the output. So that's basically the idea. So I could have written a visitor. Instead, I make a method directly in the AST nodes that will say, take a step, reduce one step. Oh, and here's the context in which to do it. Obviously, at the root, that's an abstract thing. But if I have an expression, so let's do a very simple one. Here's a variable. If I have a variable and I want to do a step, what do? I have a variable x. Well, I look it up in the environment of the context. That's the value. If I have an assignment, I'm blind. Here it is. Here's an assignment. So if I have an assignment, it's a little bit more complicated. An assignment is x assigned expression. If the expression has been reduced, that it cannot be reduced anymore, then it's a value. And I can take that value, and I can go to the environment and say, hey, take the value of that and assign it in the environment to that thing. If, on the other hand, it's not reduced, well, I can't do anything. I replace myself, the rest of the program, by a program in which that expression gets reduced by one step. So every time I have an expression, x equals 3 plus 4, I can't assign 3 plus 4 to x. I have to reduce the 3 plus 4 to a 7. Now I can assign the 7 to the x and then replace myself by an empty statement here. So all I've done is for every single AST node where I can take a step, decide what that step is. Okay, and then we're almost at the end. So here's a little program. There's an SPL context for var x equals 3, print x plus 4. Here's a custom view. Here we see the rest of the program. Here we see the environment, which is empty, and here we see the output, which is empty. And I have a couple of buttons here. The buttons here are just shortcuts for sending a message to the object, which I can do manually here as well. But it looks cooler to have a button. So I take a single step. So x equals 3 gets reduced to just 3. And now there's nothing, I can throw that away. Notice the environment has been updated, and I can inspect the environment. Of course, everything is live. I can take another step. I get rid of that guy. That was just an expression statement with a reduced expression. That's garbage. I can throw it away. Now I have a print x plus 4. I can't print that, but I can compute the x becomes a 3, and now I can compute the 3 plus 4. That's a 7. And now I can print it, and that reduces to a 7. And now that reduces, and I have the end of the program, and there's nothing left. Now what's cool, these are just composed views. So this view, this custom view, is just a bunch of pieces glued together. And here's the cool thing. Because we have a stateless representation of the program states, we have a full history. We have a back-in-time debugger. So here are the states that we had. Here was the initial state with its AST. Here's the next state that we had to execute, and then the next one, and the next one, and the next one. And we can go back and forth in time and see all the individual states. Furthermore, we can go back in time and do other things. So we can actually change this program here to x plus 5, and then execute that. So we can change history if we like. Here's a more complex example, which I think is fun. This is a Fibonacci program. So we want to compute the first 10 Fibonacci numbers, and we have a little iteration here. So the first part is boring. We're just going to define a bunch of variables that we need. I have to go a little bit slow here, but I could run quickly through it. by skipping to the end, but let's not do that yet, because I'd like to show you this particular step. Now we get to the iteration, the while loop. I told you we have single-step semantics. What do you do with a while loop? How do you take a single step from this? Well, iteration less than arg, that should be simple. We have to compute iterations less than arg. That's, oops. Okay, so here's what happens. We unfold it. We unfold it into an if-then-else. Well, an if, actually it's just an if. So the if part will just execute the block. So if the iterations are true, then we'll execute that block and then do the while again. And so on. Now let me just run to the very end. So the whole program will run. We've got the first 10 Fibonacci numbers, and now we can go to the history. And see here, for example, where did we have another while loop? Because now we can go back in time and see what happened to the other cases. So here you can also see how it's stepping through. And we actually have some 200 or so iterations before we finally get to the end. And this guy, 10 is less than 10 fails, so if false, and then we reduce to an empty block, which reduces to nothing, and then we're done. Good. So that was what I wanted to show you more or less on time. I still have a few more questions for time for questions. As I said, everything's in the download, and you'll find notebook pages explaining this in more detail, in addition to the slideshow. And of course, you can play with the system itself and modify it to your heart's content as well if you're interested, and I encourage you to do that. Okay, thanks for your attention. Lots of questions if you have any.
So the logic on how to actually do a step is contained in the node, in the concrete node. And I think I can't remember where you put together like the selection of which nodes you actually want to use. So the question like how would I change the program if I want different behavior? So I would need to assign different concrete nodes.
Well, suppose you wanted to add functions to SPL, right? On the one hand, we need to have additional AST nodes for the functions. But on the other hand, the AST nodes would also have to have steps, reduction steps defined, methods. But we'd also need to change the context, because now the context, whereas before we just had an environment and an output, now we need to have a stack of functions that are being called. So the environment is no longer a flat environment, but a stack of environments. So it becomes more complex. So that's a non-trivial extension. Some extensions could be really trivial. Probably if you have a different kind of a while statement, different kind of control statement, that would be easy to do. You just have to figure out how to unfold it in a single step. By the way, these semantic, where is it? Safari. Scholar, where's the, what was it called? Not mini Java, the semantic Java specification, the one that was used for the new type system. What was that called? I wanted to find an example. So the operational semantics are usually specified using a formalism that says what the reduction steps look like. So they're usually of the form, like for example, if I have a lambda expression, lambda x dot y, can apply to A is reduced in a single step to the body of Y, where I replace every X by an A. So it can be specified in a mathematical formalism. Same thing in languages like this. If I have an SPL program and I say, oh, if I have something like var colon equals expression, and expression is reduced or whatever, I'd invent something, then I would say, I would replace this, so expression reduces to n, where n is a var, then I replace this by var colon equals n. So I can specify all of the normal thing to do is you'd specify the whole semantics of your language using a bunch of rules, and then you could just translate those rules to your favorite implementation language. That's the idea. I didn't do that, I just directly implemented them in Smalltalk, but it's nice to have a formalism because usually it can fit in just a few pages.
Do you learn about this in theory of programming or courses? There's no course because we will also face things like that, but I will not go into this mathematical formalism. But basically, also our implementation will follow.
The two big differences are small step semantics and big step semantics. So small step semantics says I describe every single little step I make, which is kind of nice for the debugging and understanding how it works. But the big step semantics says, oh, if this expression with any number of steps can reduce to n, let's directly replace it by n. So then you can just bundle together a whole bunch of steps and take away the boring parts. And then you have very few steps, but the big steps. I decided the small steps was cool for showing you what's actually going on step by step. But as you saw, once you have the model right, I had to iterate a few times, then you say, now I know exactly what to do, and it almost writes itself. It was a very, very short implementation effort to get the actual semantics. Yep.
Why do you mean that extending the program for function support would be quite a difficult task? Couldn't it work the same just as the while loop?
No, because you need a stack of, you can't use the environment that I have. So context is an object that has 3 parts, the SPL context object. And let me see where I can find it. Oh.
You can treat a function just like a macro. Something like this, where you just can extract a little bit of code, but there is no recursion. Then it would work that if you want to have real recursive function calls, that you need kind of a runtime stack.
So this is the context, it has the environment, it has the output, and the trace, and the node, which is the ASD we have so far. But then instead of an environment, this would just need to be changed to a stack of environments. And we need to have a way of seeing where we are in the runtime stack. It's not hard, but it has to be done. And then if you wanted to add objects, you need to represent a hash of objects with object IDs, and you have to decide for a structure for objects. It's all doable. It's just that it's some implementation effort, and each thing is a little bit more work. Trying to remember the name of this small Java thing. What was it called? Maybe I'll find it. Java Semantics. Yes, I remember it now. Featherweight. Yeah, this is the all 12 versions, PDF, there we go. There's Featherweight Java, there's the paper, and there we go. You have a bunch of rules here. Let's say, which are here are the computation ones. So it looks a little bit funny, but I represent an object as a bunch of fields. So if I want to, so an object is a bunch of fields, and if I have a created object here, then if I want to access a field of that object, then that reduces to E sub I. That's all. Look up in the environment. It looks it's very terse, very concise. You have to get used to how it's written, but this specifies the whole semantics of a very small subset of Java. as a bunch of rules. Some of these are the computation rules, the execution, but then there are other rules for the type checking and so on. And each of them say, if this is true, then that's true. And it looks very terse, but I think with small effort you can read it quite easily. So what I did in the implementation was I basically implemented a bunch of rules like these. This is the classical small step, or these might be big step. I don't know what these, I think these arrows, I don't even remember if these are big or small step arrows. Yeah. Okay, yes?
So how do you handle scoping of variables if you have nested blocks?
As I said, I assumed a flat environment. So if I have a nested block, and that block defines a variable, it's just in the same global scope. Because for actual SPL programs, it doesn't matter, as long as I have no shadowing. Now, if I have a var x outside and another var x inside, then there's a conflict. And then, but since you didn't say in the description of the language, I was free to make a choice. So rather than ask you, I said, I will decide. And you didn't provide a test suite either. So I said, okay, I assume a flat environment. But if you insist, then I would have to, again, have a stack of scopes. And every time I hit a block, I create a new environment in the stack. Every time I leave the block, I pop that stack off. And that means if I have an outer variable x and an inner variable x in the block, then when I look for x, I have to look, well, the stack is the other way around. I have to look down the stack for the first x that I find. So that makes my context more complex. And I said, oh, okay, I will ignore this. So I ignored it.
But then functions would be possible?
No. That's just the environment. So I need the same thing for the runtime stack. You could use that for, no, because you don't want dynamic scoping. That's another problem. So I don't want, if a function calls another function, that I can see the environment of the function that called me. That's evil. I want lexical scoping. So this is dynamic scoping versus lexical scoping. Dynamic scoping existed in some early programming languages, and people discovered it was a nightmare for debugging. So scoping is lexical. Based on the program text alone, you always know where a variable is defined. So if I refer to an x that isn't defined in my function, it must be in an outer lexical scope. It can't be coming from a function that called me. There is one exception to this in modern programming languages that I know of, and that's exception handling. When I raise an exception, the exception handler that is invoked is the one that came from the environment that called me. It's not the lexical scope, it's the dynamic scope, and that's crucial. That's the only case I know where dynamic scoping is really used in a disciplined way. So you need to change the whole context to handle that. So you have an environment for every block, but then you also have to have a stack of environments for a stack of environments or something like that. It'll get complex. Oop, I'm going to kill myself here. Anything else? Yeah?
Yeah, maybe like this maybe a very general question. How should we decide or evaluate in which step of a compiler to do to solve which kind of problems? For example, should there already be the notion of a float as a token, so for the lexer, or should that come afterwards? Because there are many questions like that.
Yeah, so I mean, you try and do things as early as possible if it's easy to do them. So whatever makes your life easier. So trying to do type checking in the parser, it will be a nightmare, so you don't do that. But if you can do some kind of simple semantic checks already in parsing, then of course you do that. Not too many that you can do, however.
It prevents having minus a parenthesis and then a number, which is also valid. And this is in the
Yeah.
Yeah, actually, this is the funny part about it. What does simple mean? Because it's not just simple maybe to then implement it, but maybe it should also be about performance, because we want to have a good result in the end. And it's like, what should we consider when we decide those things?
There are many, many trade-offs. So there's performance in the parsing. How fast is the parsing? How fast is the compilation? How fast is the program that you produce? So there are many trade-offs there. How easy is the parser or the compiler to debug or modify or to extend? So depending on where you make these choices, they all have different impacts on all of these other aspects. So there's no simple answer, but
Also, some of these decisions then whether something is performed or not depend on a concrete input purpose. So if certain language features, whether they are used or not, so this would also, I mean, the scientific answer would be that we would have to do kind of benchmarking using real SPL programs that are written out there, right? So what are the developers using, and how do the programs look like, and how does this influence the performance of the parser? For some, I mean, you can give a kind of static answer, but for some it depends on how the programs that will actually compile it look like.
Oh, one thing that I'd like to mention about the implementation of such an interpreter, it's clearly not very efficient, but it's exactly what you might want for a reference implementation. So for the Ada programming language, which was developed in the early 80s, it was specified formally, and using a tool whose name I've forgotten, Settle, I think it was, another language, there was a reference implementation of the complete language that was terribly slow and inefficient, but it specified precisely how the programs should behave. So then you have a tool that you could use when you develop your compiler that you can check with a bunch of programs, do I produce the same result as this reference implementation, just much faster, that I compile them faster and the programs run faster. So that can be very helpful. Also because when you specify the semantics in such a way, there's so many issues that you don't care about that makes the implementation very small and easy to understand and change. Yeah, so if anybody's interested in following any of this stuff up, you can contact me easily through, well, you have the link to my website, so you can easily contact me. And if you're interested in exploring more with the environment, there's a whole community on Discord where people are working on different projects, not all related to language workbenches, but other things we can do with the platform for analysis. By the way, Pablo is a PhD student of Timo's. He's using the platform to analyze GitHub actions, or basically pulling in the GitHub data about and the configurations which are specified in these YAML files to analyze what is happening when people are using GitHub actions and they start to thrash in making changes to configurations. So that these are hints that people are having problems debugging the GitHub actions. So we're using the GT to build a whole model of all of this data so that we can explore it and analyze it. But it can be used for many, many different kinds of applications, whether you're analyzing data or programs or software or whatever. Okay, no more questions, then I thank you for attention, and I'll let Timo get to the exercise hour.